All right. First off, we'll take a look at any problems that you may have had outside of problem number 4. Like I said, we have not done logarithms yet, and that's what we'll be dealing with today. Is there any other questions that you have on any of the other problems? Once again, it makes us go back as we continue through this. It's not like we can just do some ideas of derivatives and then we don't have to worry about them anymore, like the chain rule or trig functions or e functions. We will continue to go back to them and utilize them this entire chapter, as you'll see today when we start dealing with the logarithms, derivatives of logarithms. You'll see that we're going to be doing chain rule and working with the chain rule still, so we cannot forget them. And it probably took you a little bit to remember how to deal with the chain rule. But then we have parametrics and second derivatives on the back. Questions that you have on any of the problems? All right. I'm not sure if these notes were included. I don't think these notes were included, so hopefully you printed them off. If not, I'll give you a minute if you need to print off these notes. If you need to print off these notes for for what we're dealing with today, that is fine. If not, you're just going to have to copy down as we move along. So I'll give you a few minutes here just to, if you need to print the notes that we had for today. The worksheets that I have for homework today also you'll have to print out eventually. All right, today's emphasis is how do we calculate derivatives of logarithms? How do we deal with logarithms? Well, if we have y equals the ln of x, y equals the ln of x, we want to find its derivative. Well, we don't know how to deal with logarithms right now. I could change that to log base e, and it's still not going to help us out too much. So in the form that we are dealing with here, we don't have a way of calculating a derivative. So what we need to do is we need to transform this into something that we can work with. Well, if we take a look, this is y is equal to log base e of x. If we would take it out of the logarithmic form and move it into the exponential form, okay, we have y equals log base e of x. So we have to go back and kick our brain a little bit and knock some dust off of things that we did in pre-calculus and algebra 2. How can we transform y equals log base e of x out of a logarithmic form into an exponential form? Because as we've talked about before, dealing with logarithms is not a common everyday occurrence, so we don't really remember a lot with logarithms. But if we could put them into an exponential form, we're more used to that in the algebraic world or in the mathematic world, dealing with things in an exponential form rather than in the logarithmic form. So does anybody remember, if I have y equals log base e of x, what would that look like into an exponential form and eliminate the logarithms? Anybody remember?
Would it be e to the y is equal to x?
Very good. Yes. E to the y is equal to x. This is our base, this is our exponent, and this is our value. So we have e to the y is equal to x. Now, how does that help us? Well, that helps us because we know how to take derivatives of e functions, and we can deal with this implicitly. Okay, so dealing with the derivative implicitly, I would take the derivative of the left-hand side. Well, if I have an e function, and I want to take the derivative of an e function, e to the y, well, the first thing we remember we have to do is we have to just recopy. So we have e to the y. And then we have to take the derivative of our exponent, which is the derivative of y, which is dy dx. And that's equal to, on the right-hand side, 1. The derivative of x would be just the value of 1. Now, solving for dy dx, we can divide both sides by e to the y. So we have dy dx is equal to 1 over e to the y power. Now, are we there yet? No. We're not there yet. We're not where we want to be. But we got a basis for the derivative. Now, if we take a look back at the beginning, my y value is e to the y. So rewriting this, we have dy dx is equal to 1 over e to the ln of x. So we have 1 over e to the ln of x, because y is equal to ln of x, and our derivative is equal to 1 over e to the y. But y is equal to ln of x, so we're left with e to the ln of x. Once again, going back and using our properties of logarithms, e to the ln of x can be simplified to 1 over the value of x. So if we have a function ln of y, ln of x, the derivative of this is 1 over x. So my derivative of an ln is 1 over whatever I'm taking the ln of. Now what we can do is we can apply a chain rule to this. What if I have a function in there? Y equals ln of f of x. Well, if I have the chain rule, this is equal to 1 over f of x times the derivative of f of x, whatever my function is. And this would be the chain rule for derivatives, or for the ln. So let's take a look at the ln of x, or ln of 5x. I want to take the derivative of this. We want to calculate a derivative. Well, looking at our chain rule, we have 1 over our function 5x times the derivative of 5x, which is the value of 5. So we're left with 5 over 5x. The 5's go bye-bye. And what we are left with is, once again, 1 over x. That will not always happen, but at times it will. So the derivative of ln of 5x is going to be the same as equal to the derivative of ln of x. Okay, what I want you to do is do your next derivative. The ln of x squared plus 6. Liam, what did it come down to?
Is it 2 over x plus 6?
2 over x plus 6. Is that what you said?
Yeah.
Okay, let's take a look. We have the derivative of y with respect to x. The first thing we do is we put our function, just put our function over whatever our function is over 1, or under 1. So we have 1 over x squared plus 6. And then we take the derivative of what's inside, which is your 2x. So we have 2x over x squared plus 6. Now, can we cancel? Can we do any canceling here? Can we cancel out those x's? Are we allowed to? When we have addition down there, we're not allowed to be able to cancel out those x's. So we have to leave it alone as 2x over x squared plus 6. Okay, do not want to cancel out the x's and move them to Texas. Well, what happens when we're in the idea of a log? We want to find log base 10. Y is equal to log base 10 of x. Now, when we have a different base here, or when we have different bases, this becomes a little bit more complicated. Becomes a little bit more complicated. If we would once again write this exponentially, we would have 10 to the y is equal to x. Our base is 10, our exponent is y, our value is x. Now, our problem we run into is we run into having that variable in the exponent. Now, what we've been able to do up top is we've been able to handle and deal with the derivative of a natural log. So the natural logs and the e functions are easy to take derivatives of. But when we have just a log base 10 or log base 7 or log base anything, they're a little bit more difficult to deal with. So the next thing we're going to do is we're going to take the ln of both sides because we want to get the variable out of the exponent. So we're left with y is equal to, let's try it again. Y ln of 10 is equal to the ln of x. Now to solve back for y, we could say y is equal to, we could divide both sides by ln of 10. But what we're going to do is we're going to write this as a coefficient 1 over ln of 10. ln of 10 is a number. 1 over ln of 10 is a number. It is approximately equal to 0.434. It is a number. It is like having a coefficient there. Okay, so I'm not going to try to make it messier with my ln of x by putting it underneath the ln of 10 underneath that. So this 1 over ln of 10 here is just a number. It's just like having a number 5 or a number 7 or a number 10, but it's just going to be a decimal now. It is a constant value. So when I take my derivative, we could just leave it as a constant, and then the derivative of 1 over x, or ln of x, is still 1 over x. So we're left with 1 over x ln of 10. And once again, that ln of 10 is they're just numbers. That 1 over ln of 10 is just a number. So we can leave it as, even though there's letters there, and that's sometimes the problems of difficulty students have and people have with leaving the ln of 10 there. It's like, well, I just need a number. I need a number there. I need 5, I need 7, I need 10, I need 0.4, whatever it is. But it's okay, and it's very acceptable to leave it as the ln of 10. So let's take a look at the next one here. Let's first rewrite this exponentially. Okay, go ahead and rewrite this exponentially. Like we rewrote y is equal log base 10 of x. We rewrote that as 10 to the y is equal to x. So we should have 7 to the y is equal to 2x. Take the ln of both sides. Rewrite. Take your exponent out front. Take your y variable out front. In front of the exponent, or in front of the logarithm. Once again, we're just using properties of logarithms. So we have y times the ln of 7 is equal to the ln of 2x. Divide both sides by your ln of 7. Now let's rewrite. Let's rewrite it as, once again, 1 over ln of 7 times the ln of 2x. I know it's a little bit more space to write things out that way, but it cleans it up and makes it a little bit easier to take your derivatives. It helps your brain separate what I'm taking the derivative of. Once again, 1 over ln of 7 is just a constant. It is a number. So now take the ln of 2x. Like we did up top, how we take the ln of 2, derivative of the ln of 2x. We have 1 over our function times the derivative of our function. Bailey, what's the derivative of the ln of 2x?
1 over 2x times 2.
Times the value of 2. And then these 2's will go bye-bye for us. So combining these back together, we have 1 over x ln of 7. And the reason why we put the x out in front is if you rewrite this 1 over ln of 7x times x, people will combine the 7 and the x together, which is incorrect. So typically what people will do is throw the x out front and rewrite that as x times the ln of 7. In general, if we take the derivative of any function, if you want to remember a formula in the chain rule, we have 1 over the function ln of our base times the derivative of whatever we're taking the log of. To me, I am not huge into memorizing that formula. Not huge in it at all. I'd rather just work myself through the problem as we just did, because we have enough stuff to try to remember, and to memorize another formula. How do we deal with that? I'm not too keen on it, but it's there. It's offered to you. I'd rather just go through the steps, rewrite as exponential form, take the ln of both sides, divide by your ln of your base, and then take your ln, take the derivative of your ln. To me, that's this here is just one more thing to remember, and I'm not, once again, not too much of a fan of it. All right, let's take a look at some practice here. We have an ln. We have an ln here. Let's find the derivative of the ln of the sine of x. Okay, so going back to what we did in the front, we have 1 over our function. Our function is sine of x, and then we have to take the derivative of sine. Brandon, what did you come up with? Okay, so you said 1 over sine of x times the cosine of x. So if I combine these together, we're left with cosine of x over the sine of x. Anybody remember your trig function, your trig identities? If I take the cosine over sine, what's that equal to? Anybody want to take a stab at it? Cosine over sine?
This is the cotangent.
Cotangent, there we go. Winner, winner, chicken dinner. So we have the derivative of the natural log of the sine of x is equal to cotangent of x. Now, if you left it in cosine over sine, I would accept that also. We're just expanding what we're dealing with. Let's see, y equals log base 5 of e to the x. Once again, if you want to use what we did on the front, the formula on the front, that's fine. To me, I'm going to rewrite this exponentially. So first start out rewriting it exponentially. So we have 5 to the y is equal to e to the x. Take your ln of both sides. Bring your exponent out front. Now, if we look on the left or on the right hand side, we have y times the ln of 5. I can bring that exponent out front also with x ln of e if I wanted to, or I could just leave it alone. It does not matter. We'll leave it as ln of e dx right now. Divide both sides by your ln of 5. Now with students, it's one of those things when you're dealing with these problems, sometimes students will think, okay, I got it in this form, I'm done. And they forget to now take the derivative of it because you have to do a lot of preliminary work to be able to get it into the form that you can just take the derivative of it. So they forget to take it to the next step. Well, you did all this work and I put it into a different form, and you forget to take your derivative. Don't forget to take your derivative now. So we have 1 over ln of 5. We have 1 over e to the x times the derivative of e to the x, which is e to the x. And what happens nicely here is the e to the x's move to Texas. So we just have 1 over ln of 5. Now if we take a look up here, when we had ln of e to the x, we could have brought the x out front. So you had x times the ln of e. The ln of e is a value of 1. So this just comes down to x. So you could have took the derivative of x and got a value of 1 there. But if you didn't see it, we could have just went through and maintained and still came down to the same solution. Y equals 5 to the x. Y equals 5 to the x. Well, if we would take a look at this, the most common thing people would say, well, if I'm taking, I got an exponent there. Let's just use my exponent rule. So they'll say the derivative of y is x times 5 to the x minus 1 power and be done with it, which unfortunately is not a correct answer. Not a correct answer. So how do we deal with this? Well, we have to, once again, get the variable out of the exponent. Well, how can we get the variable out of the exponents? Well, we can take the ln of both sides. So let's take the ln of both sides. So we're left with the ln of y is equal to ln of 5 to the x power, which allows us to bring the x out front. Now comes some magic that moves along. And this is a property that we talked about before, but we're going to reutilize the property. If A is equal to B, then C to the A will equal to C to the B. It does not matter what the C is, it's a constant. If A is equal to B, if these two things are equal, if I use the same base to these equal exponents, I will still have equality. If A equals B, then C to the A equals C to the B. Well, what we're saying is the ln of y is equal to x ln of 5. We are saying these two things are equal. So if these two things are equal, I can choose anything, any number, any constant I want, and use those two things as the exponents. Well, the value I'm going to use is the value of e. Why did I use e? Because I know there's a special property that allows me to deal with that e to the ln of y. And that special property was, if I have a base and a log with the same base of some function f of x, this will equal f of x. If these two bases are the same, they cancel each other out. And what ln is ln is log base e. So this here will transform just back into y. Once again, common mistake at this point is there's so much preliminary work that you have done to get to this point and say, boom, I'm done, that's my answer. Unfortunately, that's not your answer. Now we need to take our derivative. But the nice thing about this is my derivative of this here is an e function. If I'm taking the derivative of the e function, we start out by just recopying it. So we have e to the x ln of 5. And then we have to go inside, or I'm sorry, to my exponent and take the derivative of my exponent. Well, my derivative of my exponent here is 1. I bring it out front, so I have x to the 0th power, but I still have the ln of 5. Once again, we are applying our chain rule here. Are we done yet? Are we done yet? Are we there yet? Are we there yet? No, we are not. We are not, unfortunately. This is really taxing us in our properties of logarithms. If we look at this element right here, we have e to the x ln of 5. This value of x go to my exponent. So we're left with e to the ln of 5 to the x power. When I'm looking at e to the ln, once again, this is log base e. So I have e to log base e of 5 to the x. this will equal back to 5 to the x. So we have 5 to the x ln of 5. Once again, this taxes us because we have to have and recall a lot of knowledge about logarithms and exponents. All right, your turn. We have y equals 9 to the x power. Follow the same method of madness. And take your derivative of 9 to the x power. Taking our derivative, Ozzy, what do you come up with? You get it?
Not 9 x to the 9 with the exponent as x times ln of 9.
That is correct. 9 to the x times the ln of 9. Once again, logarithms, you're dealing with logarithms. You just knowing or having knowledge of the properties of logarithms helps us out a lot to be able to calculate your derivatives at that point. Questions on logarithms and derivatives of logs? All right, when I put on Classroom is a worksheet over derivatives of logarithms, along with some solutions to work yourself through for your homework for tonight. I will email you if we're going to meet on Friday. I'll take a look at what else I would like to maybe go through. I'll email the status of Friday's class, if we're going to have it or not going to have a class. I'll email you the status of that. I haven't made up my mind yet what we're going to do for Friday. I'll see where we're at in regards to coverage of the material that we are at. So you can maybe keep your fingers crossed. We'll see. We'll see how it goes. But once again, if you have questions on anything, feel free to email me. Other than that, I have nothing else for you. Thanks for attending today. Got the worksheet to do. Have a good rest of the day. Adios, everybody.